Hey guys, what's up? So, in our last video, we showed you what nucleophiles and electrophiles are. Well, today, we want to show you what you can do with that knowledge. So, sit back and enjoy part 1 of our 2-part series on nucleophilic substitution. Nucleophilic substitution? Huh? What are we talking about now? What a nucleophile is, you already know. It's an electron-rich region in a molecule that's attracted to regions with low electron density. So what does substitution mean here? In chemistry, a substitution is a reaction where one atom or group of atoms in a molecule gets switched out for another. So taken together, a nucleophilic substitution is when an electron-rich atom or group of atoms replaces another group of atoms in a molecule. Okay, but what does that look like exactly? This kind of reaction can take several different forms depending on the nucleophile, the electrophile, and the conditions of the reaction. The one we're going to be talking about today is what's called the SN2 reaction. The S stands for substitution, the N for nucleophile, and the 2 tells us that there are 2 reacting species involved in the rate-determining step. Don't worry, we're going to explain that later. Okay, so let's look at an example that should help you get a better understanding of what we mean here. What we want to do here is to take the chlorine in 1-chlorobutane and replace it with iodine. And how do we do that? To get our iodine, we're going to need its anion, iodide, which is a good nucleophile. And now we want to know what our electrophile is going to be. And the answer is the carbon atom that's bonded with the chlorine. Chlorine is a super electronegative element, which means that carbon's going to be electron poor, making an electrophile. And now what happens is the nucleophilic attack of the iodide on the carbon atom, which takes us through a transition state. The bond between the carbon and the chlorine is loosened, while the bond between the iodine is formed. And the chlorine gets replaced with the iodine. This transition state is the rate-determining step. It happens very fast, since carbon is only supposed to have 4 bonds and it wants to get rid of that 5th bond immediately. The state we see here cannot be isolated. The fact that this is a transition state is indicated by the square brackets around the molecule and this little symbol at the top right, the double dagger. And here are our products at the other end. Okay, 3 more things we need to mention. First, there's the Walden inversion. This is when the tetrahedral bond of an sp3 hybridized carbon gets flipped around, meaning that the steric configuration of the asymmetric carbon is inverted. You can imagine the whole thing as an umbrella getting turned inside out. And if you have no idea what we just said, you might want to check out our video on the hybridizations of carbon. Next, we should probably tell you about that too in SN2. Like we said, this is the number of chemical species involved in the rate-determining step of the reaction. In cases like this, the 2 things we're talking about are of course the nucleophile and the electrophile. The rate of the reaction is affected by the concentrations of the nucleophile and of the electrophile. This is why this reaction mechanism is called nucleophilic substitution of the 2nd order. But you can find out more about reaction rates in our video on the thermodynamics and kinetics of nucleophilic substitution. And finally, for an SN2 reaction to take place, there needs to be space available. If an atom or group is going to kick another atom or group out of a molecule, then it's going to need enough room to make its attack. This is why the SN2 mechanism can only occur at primary and secondary carbon centers. There's another mechanism that happens on tertiary carbon atoms, but we're going to save that for the next video. So that's good for today, huh? Alright, we talked about the SN2 reaction, or nucleophilic substitution of the 2nd order. This is where one atom or group of atoms gets replaced by another atom or group of atoms in a transition state. The tetrahedral bonds are inverted, changing the structure and the steric configuration of the molecule. The rate of the reaction depends on the concentration of nucleophiles and electrophiles. The SN2 reaction happens at the primary and secondary carbon atoms. And now if you want to know how the SN1 reaction goes, just stay right there.